Hi, you're on mute in case you're speaking.
Hi guys, can you hear me?
Yes.
Awesome. 1 second.
Yes.
Hi, you're on mute in case you're speaking.
Yeah, just give me a minute. Hi guys, can you hear me?
Yes.
Awesome. 1 second.
Yes. Shut my YouTube page. Is there a YouTube page?
Hi, you're on mute in case you're speaking.
Yeah, just give me a minute. All right, shall we start then? Okay, I just need one confirmation that if you guys can hear me, one, and if we can start.
Yes to both.
Okay, thanks. Okay, so hi guys, I'm Shashank here, Shashank Srivastav, and we have Sajay Kumarji on the other line. So today we start up with our first workshop. I guess you guys are all relaxed and excited to see what's for the next 3 days, right? So today we are looking into for the next 3 days, what we are going to plan out is what digital fabrication is all about, what are the tools that we can use, and also to understand like how we can use these tools to our benefit. Every time it's not always necessary that we need to code every single thing. There are also shorter variations to it. So we will look into laser cutting, CNC, and robotics. So these three as a main pointer. Though yes, I do know that many of you guys would know about laser, but then there are smaller joinery details which a lot of you can have fun with. So there will be some exercises which will be uploaded. I guess you have the Google Drive link. So there will also we'll put all the exercise files and also some of the files which you can which you can always you can check. So I'm also going to give away some of my files where you can actually explore and see what are the possibilities to it. So not spending much time, let's start if you don't mind. Okay, so let me see. Okay, so let me start sharing my screen. Okay, you can see my screen, right? I hope. All right, so there is a small problem with my PowerPoint. So some of the videos which are there, I'll have to go out and show you the videos. So spare me a little bit. All right, so talking about digital fabrication, what is digital fabrication? So one of the basic things about digital fabrication is about designing via computers and using a computer controlled machines to make things what we require, right? So what important thing here becomes is like designing. Yes, everybody can design, which is great. Sending it to the machine is also very simple because there are people who know how to operate the machine and to go about with it. But the idea is like, okay, designing, there are certain aspects of it that we as a designer need to understand while preparing the files, so that the person who is cutting the file or printing the file does not have to spend the time and also charge you for that aspect of it. So these are some of the things that we'll talk about today. So why digital fabrication? So as it says very clearly that to have a complex structure that we can design, and to actually see to it that those complex structures can be made. Now, how do we accomplish that part of it? Again, that is something that we will look into. Okay, so how does it help us architects is, so the traditional way of working that we always know is like we design, we make our files, we give it to the contractor is like, okay, let's get a JCB and start construction. So there are a lot of human which are involved in between of it, and there are human errors which are also involved in it. So what we are trying to look into nowadays is basically that how about reducing that middle person and the human errors. So the missing link, what we are saying is like today we are going all digital. It's not always necessary that everything can be done digitally. Yes, we are working towards that that end of it. So that is why I've written tomorrow here. So that we design, we have that design in the code itself. Computers don't make mistakes. We as a designer will make that mistake, but computers won't do that. Once a design is ready, you just send it for production. Once it's out, it's ready to play around with it. So this is what we are looking into, right? So what are the different types of fabrication techniques that we know of today as we designers can actually make use of? So from left to right, if you look into it, so the first one is welding. That is quite comparable. The second one is folding, which I'll explain what folding is. And actually folding also, many of you must know origami folding. Then the third one is punching. I'll come to what punching is. Then you have something known as cutting. So there are various versions of cutting that we can think about and know about. So one is laser cutting. Then you have subtractive manufacturing, which is more CNC routing. And then you have additive manufacturing. Now, all these techniques rely on one basic principle about material. Depending on the material, we choose one or the other technique. So understanding what we have designed, once we know that what we have designed, we also would know what material we are going to use. Once we know the material that we are going to use, we can understand that, okay, which are the techniques that we can actually look into it. So I'm not going to talk about welding because we do know about what welding is. Okay, so what is folding? So origami is one aspect of it. So what are the various ways of folding? So these are some of the examples which I've just shown for better understanding. Metal folding, we do know that, okay, how we can do metal folding. Now, what you see on the right-hand side, the clip folding technique, so these are machines which are already available. We don't really need to design that. What we need to do is just mark the ends where we want to fold, which is inside or the outside part of it. And accordingly, you can actually bend the metal. So going ahead, talking about punching and stamping. Now, this is something that many of us don't know about it, what punching and stamping is. So what it actually does is, there's a small video which I'll show you. So these are some of the examples that we might have seen unknowingly and telling each other that they might be done by laser cutting. Now, yes, we can do laser cutting in this. If you see the far right of it, all the punches can be laser cut, but laser cutting is time consuming because each circle needs to be laser cut, right? So that is time consuming. The second part is punching. Now, if you can see, the punch is literally how you punch someone. It's the same technique we used in here, where you punch a certain area into particular format. Like in this case, hexagon. In the center part, you have these circular punches which are happening. At the same time, there are holes which are being created. Now there's a small video which I'll show you which will explain better what it does. Pardon me. So here he's putting all the tools, sending the file. So this is how everything is going to start cutting. So that's your metal sheet, and it starts punching into it. So imagine this being done in laser, which will take much, much more time. The tool is simple, and that's how your end product becomes. All right, moving ahead. Cutting. So going into cutting, we do know about what laser cutting is. Now there are other modes of cutting also, which is known as plasma and water jet. We also do know what vinyl cutting is. So I'm not going to touch much more into vinyl, but I'm just going to talk about what the three differences are between laser, plasma, and water jet cutting. Laser, we've seen how it cuts wooden pieces or metal pieces or paper. At the same time, what happens if I have a much larger thickness? What do I do with it? Laser can cut about 15 mm of thickness of a material, but what happens is the laser becomes, you have to run it at a higher setting. What happens is more electricity which is gone into it, and then it becomes expensive because it starts cutting much more slower. So it's easier to use plasma in that sense, which has much more intensity for cutting much more thicker material. So if the image you can see, it's much more thicker material. Anything above 15 mm becomes easier, or let's say 10 mm for an easy calculation. Now, what happens if I have a different material? It's not metal, it's stone. What do I do with that then? So stone, if I use plasma or laser won't really cut a stone for that matter. And stone is also quite thick. It can be anything between 25 mm to say 100 mm. What do I do with that? That is where water comes into play. Now, how water jet works is there's a jet of water which is flowing, and there are granules of sand thrown into it. That mixture basically starts cutting it. There are very less errors in all the three of them. Depending on like the thickness you increase, the error also is depending on which machines you're using and which material. Errors are less. At the same time, if you see below, I've written for laser, it's precise and it's also expensive. Plasma, for varied thicknesses, you can go for plasma cutting, but it's on an average level in cost. At the same time, when I'm looking specifically for stone, for most economical way is a water jet. I can also do CNC cutting, but let's talk about CNC routing a little further down the line. I hope you understand basics of these three ideas. If not, please do let me know in between. Okay, so I'm going to go into additive manufacturing first, and then come into subtractive manufacturing. Again, why am I doing this is because additive manufacturing is something that nowadays has come up quite a lot, and we do know about what 3D printing is all about. And many of us have used it. So we do know what 3D printing is. And the most common one that we must have used is FDM, or fused deposition modeling, which uses these plastic filaments that you must have seen everywhere, like these smaller machines in your schools or cafes, where you have these filaments and you send the file, you have the 3D design, you send that file, and it prints layer by layer, right? It's as simple as this. But are there any other techniques in in 3D printing? Yes, there are. So there are two types of, majorly two types of printing. One is fused deposition. So let's assume that you have a clay. So instead of using filament, you'll use a different nozzle here where you can pour in clay or you can pour in concrete. But the principle remains the same. The principle is fused deposition, where you have layer by layer, they are printing. Going next is stereolithography. Now, this is another technique of printing where what is happening is there is laser, and which the laser solidifies certain areas of your design. And that's how your entire design comes out. So in stereolithography, SLA that we talk about is when we talk about SLA, that is specifically about resin printing. So what it does is, so there's a video which will clear it out much better. Stereolithography. Okay. Right. So this is a resin printer. What he's doing is, that's the tray, which is on the top. Below, there's a tray where he's removing the tray right now, showing us the tray. He's going to pour in the resin in here. So that's the design that he's going to print. So this is where he's pouring the clear resin. And if you see the light, what the light is doing is, the light is basically touching only those particular areas of the design which has to be solidified. Wherever the light falls into, that particular part of resin solidifies. And this is how the final output comes out. It's a very, very quick video. So again, the flexibility that you saw here right now in the end, the flexibility also depends on the design part of it. So how thin you're printing, it really depends on that part of it. You can get flexibility, flexness or solidness into it. All right. Going next. So something similar to SLA is selective laser sintering. Now, it's more or less in the same principle of where laser are actually going on top of the material and solidifying that particular area. Now, the difference is, the previous one, SLA, is more comparative to resin printers, resin as a material. Now, the other one, this one, SLS, is where I can use powders. So what kind of powder? So I can use metals, I can use nylon, I can use ceramic powders. So how does this function? More or less in the same manner what you just saw in SLA. But again, if I show you a video, you'll understand it much better. So here you see, sorry, my bad. Right, so here you see the designer, he's designing certain things which he wants to print, and he's putting it inside, all of them inside a tray. Now, each design is different. They have different thicknesses to it, so they have different properties automatically. What is more interesting is what you'll see right now. So this is just a view, what he's seeing. Okay, so if I pause this very quickly. So what is happening is, as you just saw in SLA, the base was filled up with resin. Here, the base is filled up with powder. Now, the powder can be ceramic powder or nylon powder or metal powder. What it does is, in here, going back a little bit. So there will be a head. So what the head is basically, sorry, my bad. Okay, so what is happening is, from top, the laser comes in and just solidifies a certain area of your design. That's why you see these indentations to it. Once that has been done, the left-hand side and the right-hand side, there's a small hand which comes in and flows in the material on top of it, so that the next layer can be solidified. So that is what you're seeing, the left and right movement of the hand. The laser comes down, it solidifies the material. Once that is done, the entire pieces can be removed. And depending on how the designs are happening, you have all these kind of different variations to it. I'll share all these videos as well so that later on, if you want to see it again, just to understand, it becomes easier. Right. Okay, going next. So this is powder printing. Again, it's SLS, but the only difference here is one, what you just saw previously was single color. Now, what happens if you have different colors and how do you want to go with it? Same materials that we are looking into, but then how it functions. Again, there's slight difference between, so before it was laser, now there's a bit different of how this works. And the fun part is, I'll just show you the video. So here again, you have an FFT here, the model. So again, the base is filled up with the powder. So here, this works a little differently. This works like a basic printer. So how your printer is at home, which prints your color print, you have like CMYK as a color and the other black and white. It's the same principle here. What it's doing is instead of throwing ink, it's throwing glue. Now, what the glue does is the glue can come in different, it's been mixed with different colors and it's been thrown on certain areas of the design. Again, layer by layer. Once that has been done, the layer comes on top of it. Again, it throws in. Again, the layer comes on top of it. Here, he's removing all the extra material, and this is where you have your final printout. Now, the thing is, in this case, the powder is quite fragile as such. What they do is once the print is done, there's a bath which has been taken with a binder. So it's been dipped into a binder once, and the binder, what it does is it basically collects, takes the entire print and solidifies it together. It does not take a lot of time for the binder to actually work and solidify, sorry. Okay, going next. So that was about additive manufacturing. So there are three basic ways of looking into it. Now, what happens? That is one way. That is additive. What happens is subtractive manufacturing. A lot of us, we don't know what CNC routing is. We do know what laser cutting is, and then 3D printing, and then what comes in between. There's a mismatch. So this is what I have personally seen, and that is why I'm commenting in that manner. It's not that you guys don't know about what CNC routing is. So CNC routing, for in a layman's term, if I need to explain it, we have drill guns at home where we can use the drill machine and drill holes in a wall, right? Now that drill machine is not running more than 2000 RPM a minute, RPM. Now these machines, the CNC, the spindle, so this drill bit that you see, it is very much similar. Of course, the make is different. That revolves almost around 18,000 to 24,000 RPM. So that's much, much, much higher as your normal drill bit. But the principle is the same. Like you have a drill bit, if you can drill a hole, and if you continuously go on the side, left or right, you will continuously start cutting the wall or the material wherever you're drilling, basically, right? It's the same principle here. Because the RPM is much higher, what it does, it gives you a much cleaner cut to it. So this is a very simple image that you see in front of you. And there's a lovely video which explains the same. It's one of my favorite videos. So here he's starting the machine. So this particular machine is an automatic machine, CNC machine. So here, if you see, there is like around 18 mm wood, which has been stacked together, glued together. And he's gonna mill. So these are all different kinds of drill bits. They have different purposes, what they do. I'll explain this today. So if you see, the drill bit has started and it's removing all the extra pieces of the material right now. So this particular phase is known as roughing, where all the extra pieces has been removed. Now what it's going to do is it's going to change the tool. It's going to take the most thinnest tool right now. And here it goes. So now this is your final cut, which it's doing. Of course, this video has been sped up quite a bit. This takes time. So this is your final output of it. So the beauty of CNC milling is that you can cut anything from 6 mm to up to 150 mm. And that's your maximum. So if you have a log of wood, which is around 12 centimeters or 120 mm, you can actually put it on the CNC machine and you can get some lovely designs like these. Of course, these are mountains and scenery, but that's the idea behind it. Okay, so going ahead, let's talk about robotic printing or robotic arm in general. So a robotic arm in general, if you see, can do various things. It can also do subtractive manufacturing. It can also do additive manufacturing. The thing is, so imagine your entire arm is how the robot looks like. So your arm is basically a robotic arm. Now, that is why it's known as an arm, because, now your hand, where your fingers are. Now imagine your fingers, you hold a pen. So that is one kind of tooling method. You throw the pen and you take a drill bit, or else you take an extruder. So what you're doing is you're just changing the tool on your hand, right? And that is exactly what the robotic arm is doing. So what it does is changing the tool, you can actually make it either additive as a 3D printer, or so the image that you see, this is concrete printing. So that's why the nozzle in here. And if you change that, so Sujay will talk more about like how to operate and how to deal with the robotic arm, like what are the basics of it. So I'll not go much into detail, but what I'll do show you is a small video again here, which talks about so there's a small marble which it's going to start cutting. So you see the arm has this particular tool, which is a drilling tool. Here they are checking the entire marble. So the tool part generation, which you'll learn with Sujay tomorrow and day after. How to understand and to code this. Now the tool has started. So this is a CNC tool where the drill bit is being put in. Because it's marble, that's why you have water, so that the tool does not break apart. And that's your robotic arm actually milling, doing a milling exercise. So it's a bust. You see the drill bit, which I was talking about, like how that's cutting. The beauty here is now your laser is 2-axis cutting, which is X and Y level. CNC routing is the 3-axis, where your Z axis is also there. With the robotic arm, you have a possibility where you are looking into 6-axis. So you can turn around, you can have 6 to 7 axis. So the base is calculated as a 7-axis, but the machine itself has 6 axes where it can rotate around and move around, finally getting you this as a final output. All right, just to almost end this small presentation, which I prepared for you guys was, so what we today know is about the architectural consumption that we have, right? Where we talk about the social aspects of it. And when we're talking to a client, we sell them with a story. Now, what they don't know is the production part of it, where how to use the technology, like how can we use the technology? We need to know that also as architects. We do know about the social aspects and the storytelling aspect of it, but also knowing what are the technologies available and can be used in different methods is something that, if we know, becomes easier, because then we can convince our client to come up with some radical designs and use those technologies, basically, not just 3D printing that we are nowadays using, but also using CNC for that matter. So this is basically it. So I want to end this by showing you some of the examples further, but if you don't mind giving me a 5-minute break, I would let's connect in 5 minutes again, where I would love to show you some of the examples, right? All right. Hi, guys. Just before starting, I wanted to know if there's any questions. No, then shall I continue? Not at the moment. All right, fair enough. So let me continue ahead. All right. So one of the things that is important, at least for me, is in production, knowing what kind of joineries are there, or at least some of the examples which are there, so that we know what to exploit and how to use, when to use. Um, After showing some joineries, what I'm going to do is also show some of my projects and some of the key projects which were challenging as a design, and how they were executed. So, okay, continuing with the joineries. Okay, so one thing, starting with laser. So the first image that you see right now is known as rastering. So now, what is rastering? RAS, raster. So rastering is nothing but where you take a JPEG image and you send it to the laser cutting file. And what it does is, depending on the blacks of the image. So what it does is it converts your colorful image or your black and white image into a black and white scale. And depending on where your blacks are, the intensity of the laser will be more, and where they're much gray, the intensity goes lesser. And what it does is it just moves on top of the entire material, giving you the exact image of your particular JPEG or an image. So this is something very fun, which I would like you guys to experiment whenever you can on clothing if you want. And if you have the access to a laser, please go ahead, like take your jeans, take your clothing and try testing it. It's quite a fun exercise. So this is one. Okay, going next. There's something known as stacking. So stacking, again, we must have done this multiple times, where we are cutting different variations of it and then stacking on top of each other. So nothing so great about it, but at least for you to know. Okay, so these are finger joints. That is also quite common that we know of. The problem with these finger joints is that, yes, it keeps itself stable, but it always comes out. It does not lock itself. And the problem is you have to always glue it. So it's something that I don't really enjoy using as a technique, but there's a technique which is there, at least to know that, okay, what are the possibilities to it? Something similar to the finger joint is what we will also see now. Okay, so this is known as ribbed and waffle, where you have how your waffle looks like. It's something similar on your left hand side image. Not really, but as a 3D aspect of it, yes, it is. So ribbed and waffle is something that I will be covering right now, and there's a very easy way of doing this. So now the other joinery method is where it's known as, there's no specific name for it, because what it is doing is there are two particular parts of it, where one part inserts inside and then it twists, basically. So once it twists, it locks itself. So it's a key lock detail. And these locking mechanisms can be worked out in various manners. This is just one type of a locking mechanism that you can see on your. So once I insert it inside and twist it either on the left or the right hand side, you have these two different variations which happens. So depending on where am I twisting, it locks according to that. It's a good thing because it does not move anywhere. So there's a very nice way of looking into locking mechanisms to it. Now, I will share a particular drawing for it again for this so that you can also try it. Now, this this is a clipping mechanism where what is happening in here is where these two pieces are basically straight, but once it's inserted, there's a gap here. So the gap reduces. So this particular hole which you see in here is a reduced hole. And this particular line that you see in here, that line is much more wider. So what happens is you're pressing it and then inserting the entire detail. What happens is once you press it and put it inside, inherently this will have a spring action on top and bottom. What will happen is it will go, one part will go up and the other part will go down, and automatically it will lock itself. The same thing which you can see on the right hand side, where you're actually pushing this up and pushing this bottom on the bottom and inserting it. What happens in that case, it once you push it inside the other piece, it locks itself up. So that's one way of looking at it. Now, apart from the locking mechanism, there's something known as kerfing, where you can actually take 2 mm or 3 mm log of wood, or actually more than that also if you want, depending on the cuts that you make. Different designs are also available. Different designs, you can actually bend that material just by basic cuts of it. So I'll share a file, a Rhino file for this as well, where you should actually try it out. Till the time you don't try these patterns, you won't really understand. So I'll share this file in the drive, where you can actually see these cuts, and then once you cut it on laser, you can actually play around with it, like how on the right hand side you can see these images as. There's one of my students' work where she did a small bench on the left hand side, where you have a clipping mechanism on the end of it, and in between she's removed all the extra pieces, extra material as a curved detail. So she's made two details together, and on the right hand side it's a 1:1, where this is 10 mm MDF that she's been using. So if you see on the left hand side here where my mouse is, if you see the mouse, so yeah, so they're all straight lines. But on the right hand side, if I come, and again where my mouse is, if you see very carefully, the ends which are being clipped, that is actually making there are some stresses which are happening where it's been clipping. But at the same time, what is happening is it's giving that detail of 8 mm of MDF or solid wood turning because of these cutouts. And at the same time, it's holding it because of the clipping detail. If you want, I can also share this particular drawing where you can have fun playing around with it. Okay, now that was about laser, and now coming into CNC routing, which is not much of a difference. So what we saw as a finger joinery, same thing can happen in CNC. The only problem with CNC is because, as you just saw, there's a drill bit which is there, and a drill bit, laser is a laser point focus. It's a point focus. What happens is when it's cutting, it will cut 90 degrees always. The problem with CNC routing, because it's a drill bit, it will not give you a 90-degree cut out. It will always give you a fillet or a radius of the particular tool. So if I'm using a 6 mm drill bit, I'll get a 3 mm fillet, which is not great. So to avoid having that, there's something known as, it's not known, at least I call it, as a Mickey Mouse ears. Mickey Mouse ears. So what happens is, like, I'm cutting an extra piece, I'm cutting extra. What happens is this particular part becomes 90 degrees. Just give me a second, I will try to annotate it. So this is, if you can see the red lines now coming up, that becomes your 90 degree. So this yellow part is an extra piece which I'm actually running. So in blue, so what the machine will do is go straight, then go back, then, I'll go straight, then go back a bit, go down, go straight again, and then go back again. So that's how, like an edge, it starts cutting. Right? So this is one detail, the finger joints, which is quite commonly used in CNC routing. Now, there is another detail where, again, if you see the holes, so instead of making the hole straight, annotate. So instead of making the hole straight like this, like in the previous one, what this person is doing, only at the corner, I am putting a hole there. What happens is I get a clean 90 degree. So, and in this case, it's like a key detail where once I insert it, just to hold it, I'm inserting this particular key inside it. It's a very elegant detail. Depending on how your designs are, it becomes very elegant. So keeping this in mind. Now, this is what I was talking about, the locking mechanism. So in this, what is happening is this particular part and this particular part is flexible. They can move up and down, however we want to let it move. In this particular case, what we do is that we specifically push this down and the bottom part on top, and the holes that it's going to go into. So this is the hole that it's going to go into, and this hole it's going to go into. These are smaller than these because otherwise it won't fit in. Meaning, let's assume that this is 100 mm, right? What I will do here is I will make this particular part of it as 110. Very slight mistake, but I'll make that mistake. But I will see to it that from here to here, this part is 100. What happens in this case is once it goes inside, it basically springs back again because I'm pushing this down as a clip. It will spring back again and it will lock itself up. So that is what you see in here. Sorry. Again, I'll share a drawing for you so that you can do a small test on laser and see how it works. Now, there's another detail where here I'm just doing a small pocketing in all these areas and cut an extra piece and then lock it within it. There are many more details like this that you can come up with, but I'll just stop here as such. And I will go into Rhino. All right, so do you guys have Rhino opened with you? If not, so the first, okay, so first thing is, you know what, give me a second. Yeah, so let me start with this itself. All right, so I don't know how many of you have Rhino open, but here what I want to explain is a very basic thing which is known as Bowerbird. What it does is it gives you a waffle structure. Now, what is a waffle structure, right, is what you will ask. Let me just go down. So that's a waffle structure. Where on the X and the Y axis in both the direction, you have these piece slats coming in and fixing them together. So how does this work? So let me just show you that. So it's just, I do not want to show my projects right now, but okay, I'm good to go. Anyways, so opening up Grasshopper. So I've just made two basic shapes. Nothing great in these shapes right now. But what I'm going to do is I'm going to open a Bowerbird and the plugin which I asked you to install. So apart from everything else that you see in here, the first two things, the first crafting that you see, which one is radial and one is waffle. So I'm just going to use these two for you to explain my certain things, right? Okay, so what it asks is in both the areas. Let's start with radial. Okay, so what it's asking is it's asking for a mesh. Then it will ask me like how many counts do I want to cut on one side and the other side. Thickness of the material. Let's talk about the plane on a later date. Radius on a later date. Deeper. Okay, so let's start with the first 3-4 of them. All right, so what I'm going to do is, I don't know how many of you know Grasshopper, but double clicking, say geometry. So let's take in the geometry, set one geometry. Let's say I've selected the square in here. So what you see here, the green one is what I have selected, at least I have put in. So it's become red, right? Now, I can add this directly to the mesh. So because it wants a particular geometry, which can be converted into a mesh. So, okay, this is where it is. Now, I want, let's say, 4 cutouts and 2 cutouts on one side. So I'm just going to add these. Okay, so here what you see, you don't see much what is happening, right? But at the same, okay, so I'll come back to what's happening there. So if I copy the same thing and put the same thing in the other one, which is a waffle structure, you will see the difference automatically. Okay, so what is happening is it is also asking me for the thickness. So let's say my thickness is 3 mm. There you go. So in one direction, I have 2 slider. In count Y, I have two of these pieces, and the other direction, I have 1, 2, 3, 4 pieces, right? And my thickness of the material is 3 mm. So let's say that I want to cut like 8 mm of a material. So I'm just going to make it 8 mm, and that's how I get my cuts, right? So let's say I do one side 3 and one side 1. The beauty here is what is happening in this case is like on the X side and on the Y side, I already have this working. So let's say that I say boundary. You see the 3 sides which I have, and this is 1. So what we need to do is basically just get this thing cut, right? So how do you do that also? So that's also quite fun and easy to do. So turning this thing on. I'll come back to deeper and plain what it is or what it does. So project. So right now it's false. So if I do Boolean toggle, because it's at false, it's at false. So this is going to be fun because if I say true, you see what happens in here? I get a flat piece. I just need to number it and start inserting it. And what happens is like, forget the 3D for a minute. If I keep on increasing, you can see I have 6 cuts there, right? And as soon as I'm increasing the other side, I have 4. So I have 4 here and 6 there. If I say false and I go back, I have that piece ready. So I can actually use this for cutting straightforward. I don't have to do much. Now what happened previously, so this is a waffle, which is now the other waffle is also same, but the other one is radial. Now what is happening is why you can't see anything is happening in here is it's asking for a plane. Now this particular plane is an XY plane, which is this here, this 0, 0, the start of it. Now my model is placed somewhere different than my starting point. How do I get it, let's say at the starting point, or rather let's get the area of this. So let's say because it's a cuboid, I'm going to take out the volume of it. Once I take out the volume of it, I get the center, right? Or the central point of it. I get a centroid and the volume of the particular cuboid. I don't care about the volume, but what I do care is about my plane. And the plane requires a centroid or a center point. What I'm going to do is, let's say XY. That's my plane. I'm going to put the centroid in the XY and connect that to the plane. And that is now where you start seeing the particular cutouts. Now, there's no thickness that has been added in here. So let's put 8 mm as a thickness. And there you go. So even if I increase it to 10 mm, it will keep on increasing, right? And it's quite simple. So pardon me. Right, so radially I have 7 of these pieces coming together, so I can keep on increasing. Again, the same thing is if I do Boolean toggle and I say to project, I have this. Now the beauty here is that all of them are going to go perpendicular, and there won't be much of an issue in here that you see. So these are 2 things in Bowerbird that you can play around with, right? So what you just saw right now is a cuboid. I can do the same. I don't have to do much of a difference. I just change this set 1 geometry. Now that's a sphere that I have selected, and there you go. And if I take the same sphere and put it down there, preview off and preview on. Oops. There you go. So one is radial waffle, and the other one is your normal X and Y waffle. So this is one way of doing it, right? Now, let's say that I have an Easter bunny, or there's a model that I downloaded from the internet. What do I do with that? Let's do the same thing again. Now, this particular model, when I downloaded it, it was for 3D printing. And that's why this is a STL or like a mesh model. So that doesn't matter because this guy requires a mesh. So it's important that it is a mesh. So let me just set 1 geometry in here, and I'm going to hide this. And there you go, my radial. I'm just going to quickly show what are the possibilities, so you at least you know what's happening. Now, in this case, is you have the origin, right? So in the circular part of it, I can change my origin to say YZ, and let's see what happens in YZ. There you go. It's not a bunny anymore, but at least you can start playing around with it. So in the drive, if you the drive that we shared with you, if you go into digital fabrication techniques, in that CNC laser files, you'll find Bowerbird exercises where you have these 2. You have the clipping joints, and the ribbed and waffle is something which I'll explain you right now. Show you right now. So, but I have those files ready for you, so at least you can start preparing it. Now, again, going to a larger scale, well, it's not really large in this, but so I was hoping that let's make a pavilion out of it. So what happens if I make a pavilion? And you see what is happening is I took the centroid, and according to the center, I'm putting my plane accordingly, and that's how it is. This is so strange. right? But if I just change that into this, which is a better one, again, I'm using only 8 mm, which is fine. There you go. So 10 and 10. Right, again, what I do is I make this Boolean toggle as for true. I have everything assembled. Going back, this is how it is. So this is a very simple one where what I'm doing is like I have these 3 curves where I'm lofting these 3 curves literally and offsetting this offset surface. Flip. I'm going to flip this and giving this, going to give this thickness as say 100, but let's say 25 now. Yeah, 25 is good. So that's your offsetted surface. Now, why am I showing the offset part of it? I'll explain about that in a minute. Okay, so now what is happening is that, okay, now you get all these things. Now naming also becomes very easy in this case. What you just have to do is, once you have this, you have false. You just have to take, okay, let's say curve. Okay, so I'm going to take these curves on top in here. And let's say in Bowerbird itself, I have text, which I can put. Now, the problem is the location part of it. So how do I get a location in here? Now, this is going to be a problem in most of the areas. So a technique, what I do usually is, because they are not straight and they're all in a curved manner. So you can't really find. So let's say that you find the area, right? You see where it is getting placed. But for me, this becomes easier because it's much faster. I don't spend a lot of time in here where I'm taking that, putting in that location. I'll come to the text one. Let's say that I want the size as the text size as 10. Okay, now the tricky thing is I want to start from number 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5, right? So here I need to start with the series. So I'll start with the series where this one starts from the first number in the series is 0. So I want to change that to 1. So if you see in the panel, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Right. Now it's asking me a step count. Now, many a times I can also change the step count. So let's assume that I want to make a step count of 5. So at 1, 6, 11, 16, that's how your count is going to go, right? Let's say that this is, it starts from 0. So 0, 5, 10, 15, 20, right? That's how it is. So I don't want a step count. My step count needs to be 1. Sorry, 1. So 1, 2, 3, 4, 5 is perfect. Now, after this, it's going to ask me how many values do I have. Now, the thing is, here, I have around 10 values because my slider said 10. Let's say that my value is around 30, commit change. So you can automatically see that how many pieces are like the slots have happened. So let me make it 26. So basically I have 26 values. The output should be 26 or 10 values. So this is, and the other one is 10, right? Yeah, the other one is 10, right? Okay, so let me just change this to say 14. Okay, so this value should be 14. So I have this as a value of 14. So I don't know if you can see that. All right. So but I do not know that, okay, the 14 values are coming. So instead of putting this slider, it's better for me to calculate how many values are there. How do I calculate it? The way of calculating it is list length, where I put that value, I flatten the value, right? Because when I see in here, I see a grafted value here, and I do not know how many values do I have in total. But as soon as I flatten it, I get my total as, if you see, 14. So I'm just going to take this and put it in my count value, right? So if it is getting a little too much, so I'm gonna, right. I hope this is better for you to understand what's happening and how it's happening, right? So now these series will go in my text. And what will happen is, okay, I need to graft it. And there you go. So my slider is too small. So I'm going to change this. There you go. 1, 2, 3, 4, 5. Till 14 I should have. And there you go. Till 14 I have. The good thing is once I have this, I can just bake this. It will ask me where to, so I'm just going to bake it there, and I'm going to bake this guy here, bake, and I'm good to go. So if you see that I have already baked it, I can select it. I can move this thing wherever I want to move it. Of course, right now, my number slider, sorry, my text size is really, really big. It should be smaller. It should be something like that. So but at least you get an idea like what's happening and how you can do it. This becomes easier because I can now just select it and just move it to the position I want to, either there or at one corner. Why am I saying it in this manner? Do it manually and not, I'm not saying don't do it in the code. You can always work with the code, yes, but finding one particular point in this particular curve is very, very difficult. For that, the code will become so big, and the time that you invest in making the code is not really worth it than just baking it and manually just putting it in one point. You might also ask about OpenNest. Now there's a problem with OpenNest also. That's why I don't really prefer using it. What OpenNest does is it needs curves, but it starts calculating all these points. So just for an example, and not for it to hang, I'm just going to use, let's say, 2 of them. Pardon me. Right. Okay. All right. So the first thing is it's asking me for the sheet. So let's say that I have a sheet which is 1220 by 2440. And that's my sheet, which I've already created on Rhino curve, set 1 curve, which is the sheet here. I'm going to put that into sheet. It is asking me for the geometry. I put in the geometry. And now I have 2 pieces, right? So technically these 2 pieces should go there. And if you see, okay, now flatten that down. There you go. So in this case, this is simple and it's faster. It's not taking a lot of time. So also I can change the spacing. There's only 2 of these things, which is important. Now, what happens is if I make this 22, let's see if it works. if you see what is happening is it's still calculating and it's kind of hung. I hope it works. It will work definitely, but it's going to take a lot of time. And this is something which I wanted to show, and say open nest in Grasshopper does not really work. It does work, no doubt about it again, but it takes a lot of computing power. And right now, this is much more simpler as a detail that you're seeing right now. You see only there are 2 notches in each one of them. Now let's assume that what happens if there are multiple notches like these. So just 2 notches and 22 pieces took roughly around a minute. And I have a decent laptop. Now imagine like all these pieces, what will happen to it? You might have to wait for half an hour just for it to assemble. So there's another trick for it. And usually when I have this pieces baked, I group it and place it manually again. Yes, it also takes me half an hour, but it's better for me to spend that half an hour manually than giving the computing power to it and crashing most times. I am not suggesting that openness is not great. Openness, some places, yes, it's great, but not always. Now, if you see, now I'm trying to open, okay, Grasshopper open. I'm going to delete openness because it's taking a lot of my compute power. Right? So that's basically about naming and numbering. What I also want to showcase is very quickly these. So these are sweeping. So how do you sweep? Sweep 1 and sweep 2. So these are some of the geometries which I've just created, curves basically. And why I also want to show this is because, like, if I do sweep 2 and say first rail, second rail, and then the shape of it. If you see, I have this shape now, right? And now the shape in this case, now this is an open surface, right? I need to give it a thickness. So offset surface, surface outside 25 mm. Right. Okay. So I get this. Right. Now, if I open Grasshopper, put this thing, set 1 geometry. Okay. I have this as a geometry, hide. Put that as a mesh. Okay. Things happening. Okay, there we go. Okay, for good reason it worked. Usually what happens is that it always requires a mesh. It has taken the surface and converted that into a mesh. Many a times it does not do it. So what you do is you say that I want a mesh, convert this particular geometry into a mesh, and then put that there. What happens in mesh is, like, even in this case, if you see very closely, it's a straight line. It's not a complete curve. And even if I do not connect it to the mesh, this is something which happens. So a mesh needs to be really well resolved. So one way of doing it is, what I also do is take this and say mesh with more polygons, say okay. So this is a much more denser mesh which has happened. I'm going to take that and set 1 geometry. And when I hide that, you see yes, it is straight, but it's much more cleaner because my mesh was much more denser. So this is something that you need to be careful about. And also what happens is the more your mesh is heavy, so let's say that I put this on the ground. There you go. Right. And I am going to bake this thing. Bake. Okay, and bake the other one also. Okay. All right. So I have baked this. Now, if you see, they are actually all single lines. And they are making the curve. And this usually is not a problem when it is smaller or bigger. Like laser cut will not have an issue as such, and it's so tiny that you won't even see it. Even CNC won't really matter, but yes, CNC sometimes, if it is complex, having so many small lines, sending the file to the machine becomes a problem, even for laser. Sending a file, something like this, which has so many tiny lines, becomes much more difficult. So, okay, so this is Bowerbird. This is one way of doing it. Usually I don't use this technique. I use a different technique, which is much more cleaner, where I'm actually making it, but sometimes I do require it. And when I require it, what I also do in this case is like, yes, it's manual. Yes, it is troublesome, but I'll just show you what I do with that also. 1 second. Go to top. So I'll take this and I will explode it. Yeah, you'll be like, why the hell? And then I'll remove only the ends of it. So yeah, it's time consuming, but not very much. It is depending on like how it is. So let's say that I join these two. So basically now these two are joined. I do simplify, select these guys, I join them, I say simplify. So when I do F10, okay, so it's not going straight because it's actually not straight in my model. So that is why it's showing it in that manner. This is straight, this is straight. So that has become straight. So now if, again, this one has become straight. Now this guy is being like in so many fashions, right? So let's break that thing. Let's join that, say simplify. Okay, it's not completely simplified. What I'm going to do is rebuild this to, and there you go. Yes, it's troublesome doing something like this, but it's better than the machine getting crashed in between of the procedure. I might have to spend half an hour to 45 minutes just doing this thing. Yes, fair enough. But at least my machine won't crash in the middle of the process. Right. Again, I will put this file as well for you to play around with it and have fun with it, so that you can see what are the possibilities with it, right? So let me, sorry, bad. So it's known as Bowerbird. Actually, I should just rename this to Waffle. Oops, right. Okay, so you can use Bowerbird exercise with Waffle. Actually, okay, so there's no confusion. All right. Okay, so what I want to also show is Right. Clipping joints. Right. So this is something which I have shared with you. I would like you guys to play around with this. So basically what's happening in this case is if I select these guys and move it out, you see automatically, okay, so let's put this in red. Right, so you can automatically see what the red pieces are. Otherwise, I also right. I hope you guys can see or make head into about of it. What I was trying to tell you is the distance between this and this particular one should be same. So in this case, there's a small error, but I've kept that error, or else I can change this to this here and this one there. Right now, the only thing is that this particular design of mine, I'm gonna lock this guy for a second. Okay, right. So I'm gonna take this thing and this entire piece should go in. Now the problem is if you see this piece, it's not gonna go in. So what has happened is I've made an error and I have to edit that to that, so that this entire piece can go inside. And once it goes inside, once it's in the middle area, it does the proper thing, what it needs to do. That's how it comes out, right? And there's a specific, of course, why I did that error is specific, because knowing that my mill is not going to make this straight cut. So I know that my mill, I'll be using a 6 mm mill. So my fillet radius will be 3 mm, and that's what is going to happen. And that is why that error is something which I have kept. So this is how I will literally have my piece coming out. I'm going to make this red. Right. Okay. So, and even in this case, it will be like that. So if you see what I've done is I've taken these points and I've put it in here. So what these points are going to do is it's going to make a small circle of say 3 mm diameter of 3 mm. So that's how it's going to get cut. I can do the same here instead of doing it like this fillet part of it. I can also take this particular point or this particular circle and put it here. What will happen is my final output will become like that, and my final output will become like this then, which is not a problem as such. Sorry, which is not a problem. Sometimes it's good to have this kind of a detail everywhere. So in this case, what I'm doing, because I'm using CNC, that is why I'm doing this. If you're not using CNC, you can just have this as normal. You just have to just send the file. You don't even have to think about any of these things. And let all these be 90 degrees, because laser cutting will be precise again. Right, and that way and this way. So you can just send this file for laser cutting directly and you're good to go. I hope you try this and see and use it in some of your designs. That'll be really, really fun. All right. So this was this. Okay, now going to, I'll do, okay, let me take a 5-minute break. Before doing a 5-minute break, I'll just run through some of my projects very quickly. This one that you see is on the ceiling, and this is CNC cut. there are these spacers made out of pipes. If you can see in here, there you go. That one, those are pipes there. That is a pipe there, and that's a beam. So between the beam, these pipes are holding it. And it's a very simple technique where on the ceiling, I have this particular hook, and on the hook, I have this particular pipe, which is running, which you see in here. And that hook is just holding it. So it's quite an easy technique that's been used in here. So this is laser cutting, which you can do, which we have seen multiple times in our life. This is behind a bed. Again, laser cutting. So this is CNC again, routing because it's 8 mm. And this particular chair, the white chair, is also CNC cut. I'll share you this file. This ceiling that you've seen already, this is also a waffle structure. This is made out of cardboard, and there are these pieces in between which are wood, so that it can give some certain strength. So at every 4 feet to 5 feet, we had this grid of wood, and in between of that, we added this cardboard pieces in it. The dining table, again, a waffle structure. Waffle is quite simple to use. So waffle you'll see quite a bit in most places. Now there is a study desk where part of the table is being stacked on top of each other, and the other leg is waffled. So this was a very fun design which happened. So if you see on the right hand side, the left hand part of it, you'll see every piece are being stacked together, and the right hand side is being like a waffling together. So I'll show you this particular design, how it was made, so at least you know. Again, stacking, variations of what you can do. This is a file which I'll share with you so that you can have fun with it and see how so I like using just basic joineries without any glue or a screw. So you can use this, cut it out for yourself and see how they function. They all come together. This was another exercise which we did for a restaurant with some students. And you can see behind like how closely all the pieces were cut on the CNC machine. These are not laser cut. They're all CNC. It is designed for disassembly, yes. Again, you saw the ceiling. Now the entire reception table is in Korean, and again, you can probably see these pieces, small pieces in here, which are being stuck together. The Korean has been like the sheet of Korean were cut first in these circles, and then each piece were joined together on site. So this was fun as an exercise. This is another project which I'll show. A very simple method where we usually think that with computational design, we can make these. Yes, we can, no doubt about it. But we as designers, we always fight with time and the costing aspect of it. So when your client just gives you a tight timeline of literally 1.5 weeks for design to execution, and falls in love with a design like this, how do you actually get it done within 1.5 to 2 weeks, 15 days time? So that challenge, so that is where you can't just open Grasshopper and start designing and doing these things. You have to be creative. So I'll explain you that part of it, like how creative we became. This was a competition. This was completely 3D printed, first in India 2016. Again, it was in parts, but it was assembled together. There were 12 parts in it, and it was assembled together. It stood and it took weight. So that was phenomenal. And this was another competition in 2016, which we won. So here again, what we tried doing was to take in all the techniques that we have learned. So laser engraving on Korean on top there, so 3D printing here, and CNC, two-way CNC milling, and metal bending, and welding. So all those techniques came together. So the pink one that you see, that is two-sided milling. So both the side, so one side you take out the material, you turn it around, and you take out the material from the other side, and that's how you get a thin section out of it. And this was made in wood. The green was in wood, and the top part also was in MDF, the brown part of it. So coming to these ideas, so this is where design is important. Like, you have a design, you have a wonderful design, then how to even approach it. So I'm not so sure if I have this file. If I have this file, I'll show you how this entire section works. So otherwise, in this drawing, it is seen. And that's basically it. So give me 5 minutes, then we do a small exercise on waffling. And also I'll share some of my projects, the projects that we just saw, but in design, which I'll also be sharing with you. Right. Now I'll stop sharing. Okay, give me 5 minutes. Thank you, guys. Okay, sorry. Okay, hi guys. Let me see. Give me a second. All right, so let's do one thing. What I'm gonna do is the code which I shared with you. I'm gonna make the same code, but in front of you with you guys, so at least you know what's happening. It's a very simple code in this case, but there's pardon for the 10,000 plugins. No, so the code is basically very simple. You can do the same thing with Bowerbird also. But here you'll see there's a slight variation to it. And sometimes when you have different designs, and how can you tackle those designs is something that which I want to share with you. Right, okay. It's gone. Yeah. All right, so yeah, it does take time, thanks to all my plugins in here. But okay, so let me just open that. Ripped and waffle is what I had have shared with you guys. So at least let me just show you what it's doing. Okay. Okay, so what it's doing is this basically, but this curve can be anything. So let's say I make a curve. Okay, the curve is okay, right. So and let's say set one curve. And there you go. So, okay, there is a small error which is happening, but at least you can see how it's changing, right? And this is precisely what I want to talk about and like explain about it. So it's actually not a very complicated code in this case. It's actually very, very simple. What's happening is that if I just say new, okay, so let's start with coding this entire thing. Say set one curve, right? What I want is I want like this kind of a detail which happens. So this is my center, this is my center, and all my pieces needs to come from there, come from this side, right? So that's the main idea behind it. But this curve, the central curve, can be in any direction or any shape for that matter, right? So the trick here, what I'll show you is what's going to happen is a piece which is going to come. So The piece which is going to come, so this is one circle, and then the piece which is going to come. So I'm going to divide this part into two parts and then cut it out. So the same waffle idea in a different manner. Well, you can do it in multiple different ways. But let's see it in this particular fashion, like how I can get it done, right? So, okay, so curve is being selected, right? So now I just want perpendicular curves, perpendicular frames. Now what this is doing is it's taking the curve and dividing the curve in multiple frames. So you can see that the XY direction of it. So I am going to say, let's say 5. So these are all going to be in one direction. Okay, so this is this, right? I'm going to make a circle. Okay, I need a plane, which is this one, and I need a radius. So let's say my radius is 25, and let's see what happens. Okay, so that's my 25 radius, right? So let's assume that this is my inner, or let's say outer circle. Outer. Right, so this is my outer circle radius there. So these are number of number of division. Right. Okay. So this is this. What I also want is half the size. Let's say half the size of my radius. Half of this is there, right? So whenever I change this, or let's say not half, I say 1/3 of it, right? So divide by 3. Okay, now 1.5, let's say that. Okay, sounds good. So whatever changes I make according to that, that's my inner radius, like 1.5 times of it, right? So it's easy for math calculation. So I'm going to make it like that, right? My result, if I want to know what my result is, let's say 22.6634 divided by 1.5, right? Okay. Bifocals, no. Okay, so let me just see if I can download bifocals very quickly. You have? 1 second. Okay. Okay. Better? Cool. Right. So I hope you guys can see it and I'm not too very fast. Anyways, continuing ahead. So this is done. So now what's going to happen is that I do want to make some horizontal lines, right? Now, okay, let's change this value a little bit. The fun part is I can keep on changing this curve, right? Anyways, now let's say that I want to divide this. Divide curve. I'll tell you what I'm doing and why I'm doing. Okay, so this is my outside curve, this is my inside curve, and I'm gonna divide both of my curves by equal number. So right now there's a default value of 10. So let's say my default value is 6. right? So at least I know it needs to be equal. So outside part of it, so I'm going to give some distance. So at least we know the top part is outside, the bottom part is inside curves. Right. So what I do want to do is if I make a line, and this is going to be fun. If I make a line from these points and to these points, so this is exactly what happens, right? Which is perfect. It's not at all a problem in this case. But what I do want to do is that I want to make a line between this one to this one, meaning meaning from here to there and here to there. So this is what I do want to do, right? And how do I do this thing? So there's something known as flip matrix. And what flip matrix is going to do is, I'm just going to add that. So instead of going 0 to 1, it's going to go 0, 0, 0, 0 everywhere and 1, 1, 1, 1 everywhere, right? So, okay, so how does that happen? Okay, so very strange. Not do that. Okay, my bad. Pardon me. Oh, flip matrix is there. Okay, fine. This is this. How these things happen. Okay, I'm gonna do. I'm gonna cheat. Oops. And just see what happened. Oh, right, I missed one step. My bad. There you go. So what mistake which I was doing was is the value. So let me show you that point list. So my points are basically size. So if you see, I have 0, 0, 0. Okay, lesser number, better. Okay, let's just have 3 for now. So you have 0, 0, right? So I wanted to take all my zeros together. And what I was trying to do was that I was just joining 0 to 1. So when I say line, I'm doing this is 0, all my zeros goes together and all my ones goes together, and that is why this is happening. So that is a mistake which I did. So basically what I wanted to do was interpolate the curves, and these are how I'm interpolating the curves. So in this, so what's happening is I'm getting this kind of a view towards it. Right now, what is this view? Nothing but when I merge this and say I loft it. So before lofting it, I am just going to check something. I'm going to check that this value and this value, it needs to be 1 and 2. So what I'm seeing is like I have 3 because I have 3 of them, which I need, right? So I'm going to pull this out. So I have 3 values and each of them have two branches, right? Or 2 curves rather. So this is exactly what I want. And that is what is what I was going to require, right? And this is what eventually I do need. So this is one part of it which I do need. So I'm just going to group it for now. And these are the two things which I already have, and I do need this also. So what I'm going to do is copy the same merge and say boundary. And this is the boundaries that I'll get, right? So I'm going to hide that guy, hide this one. And because I'm keeping it in the center, so I don't think so. So there's the outside part of it, there's the central one of it, and then there's the bottom part of it, right? If you see, they're just basic simple commands which I'm using. There's not much of a difference which I'm doing there. Right now I have these edge surfaces, so these are my edge surfaces, so I don't require preview off. Okay, so in the end what I do need is the inner circles. So let's say inner circles, right? Oops. Okay, my bad. Right. And these are my outside strips. So less confusion. So now these are done, right? Now, what is required is that I need an intersection, and I can do either do an intersection, or which I already have, I can make a line between these two, which I was making beforehand. Right, so I'm gonna make this one and this one. So this basically what I'm doing is finding the intersection out of it, and that's gonna be important for me. So that intersection can happen anyhow. I can actually so now this is my intersection. Actually, no, I don't like that. What I'm going to do is, like, my intersection is point to point. I want to extend it. So I'm going to extend my curve in both the direction. So the type, I need it as a line. Yes. Start, let's say I will extend it by 5 mm from on both the ends. And if you see that on both the ends, it's been increased by 5 mm, right? And this is going to be important for me. And here I'm going to say, so this is no. So this is finding intersection. Right. Okay. So that's basically done. Right. Now, because I've found the intersection, I would like to know the midpoint of it. And once I know the midpoint of it, I would like to break it. So basically, that's my midpoint, curve midpoint. I'm going to take that curve and I'm going to shatter it here. I did not shatter for some odd reason. Okay, which is very strange. Why is it not shattering? You know what, I can do another thing in here. I can divide the curve again. It's a bit of a messy thing. Shatter is not working for some odd reason. Okay, my bad. So basically what I want to do is I want to keep the two of these things different. So one is different. So this is one and this is second one. So this is what I want to do. So in this case, I'm going to do it a bit more rudimentary. Divide the curve into 2 parts, and that's what I have. All right. So it did not do it with midpoint, which is strange. Okay. Now How many segments here? 90 segments. Where do I have 90 segments? Right, okay. So I do have the shattered files with it. So what I'm doing is, once I've extended it, I've divided that into two, I've divided the entire line into two parts of it. Once I have that, I am using those tangents, right? Okay, so basically the shatter command, it requires a parameter to split. So basically it requires a point where it wants to split. So I'm giving that point. So the curve, the point, and it's shattering, right? So now if I see, I want to say dispatch. And when I dispatch it and I say TRU true, oops. And false. I'll explain what I'm doing. So if you see, it's made a mistake automatically. So it shattered there, which is wrong. Right, okay. Parameters to parameters, my bad. Right, so if I see my midpoint, yep, that's my midpoint of the curve. And half have gone there, half have gone there, right? And this is what is important for me to do. No, so, okay, I found the intersection, and in this, what I'm trying to do is, after finding the intersection, I am dividing. To length curves, dividing. So basically I'm splitting or dividing or splitting. Let's say splitting. Splitting the curves into two, right? And now I have A and B. So I have one part of it and I have the other part of it, which, let's say, put it there, right? Okay, so now what all do I have? I have this file, I have this, right? Now I have these two. So what I'm going to do is, before understanding what goes where, I'm just going to say pipe and connect that. Now this is going to be fun. Now here is where my material thickness comes. So the radius basically is nothing but half of my material thickness. So let's assume that 18 mm is my material thickness, right? So I say material thickness is 18 mm. What I'm going to do is I'm going to make an expression, x divided by 2, and radius, because it needs a radius, and I am going to give a radius. I'm going to give what I know is the total diameter, which is the material thickness, in other words. So okay, so again, to explain what I'm trying to do is, basically, if my material is 18 mm, right, my diameter will also be 18 mm. And that's basically it. So that is what I'm trying to do in here. So I'm dividing that into a half, which is 9, right? 18 mm. So 18 mm is too much in this case. So let's say 8 mm. 8 is also too much. 4 mm, right? Okay. So oops. Okay, so 2. Right. Within this, it is asking me for caps, and I'm saying flat, and I'm saying flat again. Right. Okay. So what I'm going to do is I'm going to open this up. Expression, right? Okay. It's a very simple expression. I'm just doing x divided by 2, right? where this is my X, and I don't want this. Why is it not doing it? Variable X, that's right. This is the number divided by 2. Okay, multiply. That's interesting. Invalid name. Okay, so delete. So the expression in here is nothing but divided by 2. Right, so I'm just going to remove the expression from here because it will be double. So what I'm doing is converting my diameter into radius, and my expression thus becomes X divided by 2. So whatever my material thickness is, that divided by 2 is my radius. And that's basically what I'm doing. And I'm keeping my caps as flat. You can keep it rounded, doesn't really matter. You can keep it flat is also fine, right? So that's that. Now what is happening is these two things, right? What I want is that from the outside part will have the inside cuts, meaning if I, okay, so let's do this. I want this to happen. And I want the inner circles to have cuts like that, so that from outside I can insert it, right? So how do I do that? So let's do one by one. And even if there is a confusion, I'll show you exactly what's going to happen there. So I'm going to take that one. I'm going to take that one. So I'm going to say intersection. Where is it? Okay. Right. Okay. So let's say solid intersection. Okay, so let's say that is B dot A, and this is B dot B. Let's see what happens. Okay. And let's not do it. It did it, but it still did not do it. Okay. Trim, right? Okay, this is my shape and this is my cutter. Yep, there you go, finally. Okay, so what I'm doing is I'm trimming my solids basically. So this is what I want. So in this case, what will happen is my outside can go, right? So how does my outside look like? So basically the same thing I'm doing what we just saw in Bowerbird, but much more in a lengthier process. But you do require this kind of a technique sometimes. And there you go. So what I'm doing is, again, the outside one. So this one, I wanted to cut from here. So this is what I get. This one, I want to cut from inside. So this is what I get. So in total, this is how I get my pieces. It's as simple as that. So now the beauty here is because I've coded it, number of slider, which one is this? So this is 3. So this is the outside one. So I've not named it. So outside, oops. Outside strips. Right. So let's say keep on increasing that number of strips. There you go. So I have 7 pieces. Right. And I have these pieces in here. Now, the circles in here, right? So I hope you understood what I've done in here, very simply put. So again, going back, I have a curve. I'm dividing those number of curves because I need a certain number of circles into it. So basically, okay. So basically I have these. So I need these ones in between. So now I know that, okay, what it is. Now these shapes can be different. You can play around with the outer shape. So you can play around with this outer shape or the inner shape as you wish, how you wish later on. You can map certain things onto it by orienting the geometry. We'll orient the geometry right now, so you'll see what is going to happen. And then so you have this. So you have the inner circles to it, which is great. Now, what I want to do is I want to make the outer strips in here. And so what I'm going to do is, because I have the inner geometry, I'm going to divide the outside circle and the inside circle in the same number. Once I have divided that, I'm going to make a line around it, basically. So once I have that, so I have my strips. I can loft it and I have my strips in this particular manner, which works beautifully. Now I have these two. Now they both are successful. They both are working. Now the problem is, how do I insert? I do know that my outside strips, which are these strips, needs to go from outside, and this one needs to remain in here, meaning the inside strips needs to have holes on the outside. And so in this case, what I'm doing is I already have my sections or intersection rather. So once I have my intersections, I'm going to extend the lines. I'm going to divide those lines into 2 parts, which is one part is here and one part is in here. So there are 2 parts which are going to be there. So it's easier to understand like this and like that, right? So there are 2 parts. So what I'm going to do is going to make a pipe on both the sides. Now, because I already know that this one needs an outside one, so I need to select the outside pipe, because that is going to be trimmed out. And that's how I'm going to trim it out. And I have that. Once I have that, I have the inside also. So now these are all going to go from outside, if you see cautiously, right? So there is a basic principle of what Bowerbird is doing. And because you have, now this is a curve, and Bowerbird cannot work in this particular curve. You try however you want to try, you will not succeed, because the center line itself is changing. So it needs just one axis and one straight axis. It can't work on a curved manner. And this is why it is important that to know this. Now you can cut this in vinyl cutter instead of using laser cutter. You can use vinyl as a material or paper and actually make it at home. This is very simple. You can actually print it out, cut it, and make it. So you just have to change the material thickness to, say, like 1 mm or 0.5 mm, and you can actually cut it with paper. So that could be fun as an exercise. Okay, so 1 second, it's doing that. All right, that's 0, my bad. 2. Right. Okay, now the next thing. You know what? I'm going to save this. Right, now I have these circles. Now I want to, I want to place it on the ground, right? So that I can go for laser cutting or printing or whatever. So orient, I'm going to orient it. So the beauty here is I have my result, which is my geometry. Now the source. Now, if we remember, we already had these frames and I'm going to take those frames. And now it's all going haywire, which is fun. Now I'm going to say my target is XY, right? So it's going to go there. Now, here, this is going to be grafted. And there you go. So now the problem, what has happened is, if you see the geometry is 5 because I have 5 frames, which is like, if you see the 5 locally defined values, which is right. And I have 5 results, which is perfectly fine, which is perfect. Now, what has happened in here is that it's oriented all of them on top of each other. But the beauty is that if I take my, if I move it, move each one of them. So now if you see, I'm just moving all of them together, right? So what I want to do is move each piece individually. So for just you to know, where's my tree? Okay, so you can see there are 5 branches, right? 1, 2, 3, 4, 5, 5 branches, right? Okay, so what I'm going to do is I'm going to do series and I'm going to say move it in my X direction. And my start point and my step count would be, say, same. In this case, what's my diameter? Outer circle radius. Okay, so radius is what I'm doing, right? Okay, so I need a diameter, so double this thing. So I'm gonna say into 2. That is multiplied by 2. Copy that. Get it here. That's going to be my step count and my starting point. So basically what I'm doing is by 68, or let's assume that I am not going to do that. I'm going to say 100. Step count, sorry, my start is 0, step is 100. Count is, as I told you last time, list length. I'm going to take that list length, flatten it, number of count, right? So what I'm going to get is 0, 100, 200, 300, right? Now I'm going to move that value. So each value I need to move, meaning I need to graft it because this is going to be straight. I'm going to graft this thing. And there you go. So each value is different. Why am I grafting? So if you see in this, you already see that each branch is different, meaning even here, each branch needs to be different, but it is single. If I graft it here, I have all my branch different and that works well. So this two needs to be equal. So one branch will go to the other one. So I hope you understood that part of it. This is how what I'm doing is I move my geometry. My texting becomes easier in this case again. So now this is how I'm placing it. So this is my final output, which I needed, which is this one in here. Now I'm taking that. The first step is to, 1 second. Okay, my first step in this case is to put it on the ground, right? So that's basically it. So I can't really copy paste it technically. I'll tell you why. There's a small thing which needs to be done in the other one. So once I have this, now I need to give the text values to it. So going back to Bowerbird location. So geometry, I say I'll take the area of it. I take the centroid of it, and again, I'll need my series, but my step count will be different. And I would also require my list length. So this is my count. My step is 1 already, which is there. So I'm not going to change that. I'm going to change my start as 1. Because I want to start with number 1. Let's say 6 is my size, and these are my numbers there. Now the problem is, there you go, because they are all flattened in here, so it needs to be in the same manner. And this is how I have my numberings also done. I've not placed it, but I can roughly place it like this in here. So it's already there. Off, right. That's very strange. Center of these. That's interesting. All right, so this will also be on. And all right, this is not going to be on. Right, okay, fine, my bad. So this is for texting. Right. Okay, so this is understood now. So my main are this and this. Okay, so this is there. Now the problem with the other one is they are kind of curved. Actually, they are curved. So I need to unroll it. So I'm going to use unroll command. You can use that unroll command in params as well. All right. So result mesh or brep, I have unrolled it, and these are my unrolled surfaces. Once I have done this, I don't need the orienting part of it. This is already orienting it. So curves to unroll, points to unroll. I don't need to do any of these text or text point to unroll, right? What I'm going to do is take this unrolled version directly and put it in my geometry. So again, what's going to happen in here is, there you go. Now the problem is that this is going to be arbitrary. And so they're all going to be arbitrary. And again, if I just copy this thing, which I told you last time, it's not a very fun exercise, but well, your numberings are outside and inside. In this, you can play around quite a bit. So you can just hide these two for now. You can still play around with it if you want to, and get it much more closer. But this is just a technique which I'm showing you, which is easier. Now you can play around with this and explore more and how you want to go ahead with it. So this is your very basics of like how you're texting it. and also how you're positioning any unrolled, any surface which is a two-way curve. So you just use the unroll command in here and place it on the ground. Now, the thing is like, which is my one? Where am I starting it from? Right? And it's a good question because even I had the same thing when I started doing it. So again, so when you see these starting frames, there's something known as point list. And it's quite powerful as such. So as soon as you put the point list in here, at least the first part of it, and say my size is 15. So I know my 0 or like 1 is 0, 1 is 2. So because here my numbering is different, right? Because I'm starting my numbering from 0 itself. No, sorry, starting my numbering from 1. So if I do this 0, then of course this will be 0 in here, meaning let's do that 0 in here. It starts from 0. And this is how it's going to look like. So 0 is 0, 1 is 1. So 0, 1, 2, 3, 4. So at least I know like, okay, where it starts from. Now, the same thing with here, point list. So here. So that's my starting point, right? I can also use this because I'm doing my divisions. So when I start this, I know that, okay, my 0 is there. How do you point this thing out, right? So another way of doing it is like, you already have the circles which are in here. And the good thing is if I divide it, so this is here. Okay. The good thing about in this case is that because you have these 0 values that you see, the 0 is a central line and the 0 which is on the far right of it, right? When I'm placing it, it is exactly going in the same manner. You will ask me, how do I know that? It's also because of the, what do you call, the plane that you see in here. So you just follow the plane and follow the plane in here because the plane is, the red line is the X direction, the Y line is the, the green line is the Y direction. You have that. So you understand where it is going to go. And it's the same with your number 1, 2, 3, 4. Why don't you try this out? I've already saved this. I'm gonna put this also. And because we have half an hour, what I do like to run through is very quickly the other projects and the files which I'll share with you. So at least you have a better picture of the other things as well. Okay. Right. I don't think so. I have a picture of this. I do have a picture of this. Right. So this is a very, very simple technique that was used in this case. So what I'm doing here is this is cut in wood and then there's 3D printed and then glass on top of it. Very, very simple and basic thing, which was supposed to be done for a client of mine. And very simply put, so the gold that you see, it's actually ABS plastic and it's FDF printing, but then we just spray painted it in bronze and it still looks great. So again, there's no screw or glue used in this. And the preparation was very, very simple that we just saw the bowerbird example and even like the cutting example right now. So this was completely done manually. The shape was cut and I'm going to use Gumball right now. Right. And so this is literally how it's going to go inside, right? So once this is going to go, the beauty here is once this is assembled in here, and I hide that one, these pieces, which was, yes, of course, these are Grasshopper Voronoi. What they are doing is nothing but they are going down and fixing exactly in the position. Right now I'm like doing it manually, but I do have it. 3D abstract room. Right, okay. Oops. Right, okay. There you go. So the beauty here is that these pieces, they just clip in. So what I did was, in this case, I made the surface, created the Voronoi, used Bowerbird, and got the shape out. Once I was done with it, this was done manually. If you see like how dense the mesh and the smooth the mesh is. Here what I did was I made the surfaces, converted into a mesh, and then joined the meshes together, or Boolean union the meshes together. What happens in that case is at least I have that flexibility and know-how of getting the pieces precisely right and at the same position. So there won't be any error for me. So that was how this particular part was done. So it's something that you could try also working with it if you have a project, something similar to that. Okay, so very quickly, the chair file which I'll give you, which I'll share with you is, I think there's an exploded view with all the renders and things like that. Okay. Right, so this is an exploded view, what you can see already. So sorry, not this one, this is the wrong one. Right, this one it is. Right. So in this, again, like all these pieces, you can see what is happening, like how this is going to slot in, go inside there, and these are going to slot in within it. So even if I want to play around, so this is going to go right there when I'm placing it. When I'm taking this, you can always see the Mickey Mouse ears always, and even in this part of it. So I'm just gonna take that thing, and there you go. So you see how it fits perfectly. Now, these also fit perfectly because the drawing is made in such a manner that these have no tolerances. They fit in like you have to hammer it, and that's how they fit in basically. So this is a very interesting technique. What is happening is I'm going to put this first, the leg first, and then I'm going to use this and put in this thing. Sorry, so I'm going to put this thing, these two outside. I'm going to assemble it outside and then put it together. So this itself is a very interesting locking mechanism which is happening because these two are locking within each other. This two is locking within each other. This two is locking within each other. You don't need anything else. So basically, again, here I place these two together. The blue is acrylic. That's why it is seen in that color. There are different materials again. So, and that's how it is getting placed. Again, this one does not require a lot. So it's just being placed here. That goes in there. And this is a normal way of putting this thing down. So this goes down very easily. And that's basically it. Again, this is a kind of tricky because you can't put this seat before putting this. So you have to put the legs first with the backrest, and then all the pieces come together. So This is the file. One second. I don't have a top view. I do have a top view. There you go. So there's a file where I can cut like in 1 8 feet by 4 feet panel. You can cut 2 bar stools out of it, and the seat is being cut out from a different piece altogether. It's been cut out from acrylic. So this is this. Quickly would like to show you this. Okay. So this is so very simple. It's so pathetic in one way, because again, this is Bowerbird. You can see how this is so simply done. So I would encourage you guys to try out something, and so you can see how each piece is being placed within each other. It's quite fun to do this. So this is one. Then I'll show you the directors table. Right. So this is where there are two different techniques coming together. And because of the size, there are colors, so at least you can understand like what pieces are going where and how they're going where, because it was quite challenging even for me to even understand what's happening. So once the design was made, I know which leg is going to be stacked, which leg is going to be waffled. Here the thing was that was very important for me to understand was to take all these pieces, because they're all big pieces, and how to make the weight, reduce the weight. So these are also the thoughts that you need to think about. Now, all the purple pieces that you see in here, sorry. So they are in 2 parts. So if I select, so if you see that, they are actually in 2 parts, and they are actually staggered. So each piece can go in a different manner. You see the buildings in between, that is being cut when these sections are coming in between. So what happened was, like, I made one part of it. So okay, so that's your basic idea, right? That is what you wanted. So what you do is, like, you just make a waffle with Bowerbird very quickly, and then you have one leg. The other leg, then you can start making it. So construction. So let's see the construction part of it. Okay. So this is the construction for the legs. Okay, basic idea. But these also has drawers. So right. So first rule, or do the simplest thing and get it over with it. So I got these simple things done. Right. So I know how the stacking is going to work. So I started calculating how my middle sections are going to work. So which area I need more strength, which area I don't need more strength. So the horizontal, so apart from this part of it, what was important for me is to understand my connector. So once I have this, so roughly I know that, okay, how my connector is going to work. So that is how I'm showing the connector. So the waffle is simple. It's not very complicated. I just need to know that, again, if you see, I'm not cutting anything, and this is not in Grasshopper. The Grasshopper would have killed me. But now, because I know how this entire thing is working, I can make a Grasshopper file. Again, if you see, I'm still developing these connectors right now. I still don't have the pieces ready. But once I have them, then I'm doing the slotting mechanism. and my slotting mechanism has been ready accordingly. Here, I also need some kind of a support. So I have a support in that manner, which is a very smaller support. Every now and then I'm checking out how my thicknesses are working, if my thicknesses are right or not, because otherwise they don't work. And you'll see that how these cutouts are going to come. They are coming because I'm checking like how these pieces are going inside or outside. So you're always time and again checking each and every part of it. So once those things are ready, you have your final lookout into it. Okay, of course, there'll be more cutouts because what I'm doing is there's a drawer which is also being made within it. So there's a drawer which is being made within it. This is highly complex, where there was a lot of details where had to be looked into, seen that all these pieces are cut properly. There were prototypes which were made twice, small scale prototype, just to see that there are no errors and they're working properly. Once they're all ready, then these pieces were sent for production. And again, as I told you, that because all these pieces where this entire design is made manually, even the pieces were assembled manually, as in like I did not use Grasshopper to assemble it any which ways. All right, so that was that. One last thing before we go, we end. The ceiling that I just showed you, the last image. Right, so this is a ceiling that I had showed you. It was a restaurant project which we did, and it was fun because it's a really tiny area, and so that's basically the roof of it. So floor, let me just do the walls. So that's how the space is. It's not a massive area. So the thing was in here, when we have 2 weeks to deliver, to also to finish assembly with the design, like how do you do such a kind of a thing? The idea was very simple, that we had these motifs, which motif needs to flow in a particular manner. That was very clear. And it was also clear because there were certain elements, like there was this duct which was going, so it has to cover the duct. Then there are columns and there are beams which are coming, so we need to cover those areas. So that is how the flow was going to go, which is very simple. It's not very complicated when you think about it. Once this was set as a rule, it became easy what to do with it. So we already knew that, okay, we need this particular, some kind of a pattern. So what we did was, before going ahead, doing anything, sorry, here shaded, made a surface which is much more larger than the entire space, because there is an error which is going to happen, which I knew about it. So I just wanted the surface to be much larger. Then the best and the most easiest part is that what I'm going to do is, I already did some testing in one day about the size of each piece. What I wanted to know is that, so I had 1, 2, 3, 4, and 5. There are 5 geometries which I wanted to know. Right? Okay, great. But what I want to know is how many pieces are coming in totality. So once I know how many pieces are coming, it becomes easier for me to calculate. What I did was I just took one basic module and copied it at certain intervals and just randomly copied it. And there are like 875 pieces. I took all those 875 pieces and used the command flow along surface, and just took this entire grid and put it on top of it. Once I have that, I can delete the pieces which I don't want and keep only the pieces which I want. And when I select it, out of 875, now I have 497, which is roughly around 500 pieces. Now I know I need 500 pieces, right? And I have 1, 2, 3, 4, 5 different geometries. So each piece 100. That was as simple as this. So it became so simple for me to make this file. It took me half a day to calculate it and assemble this in one sheet. And I just needed to send the like 10 pieces. I just have to calculate that. Okay, in one piece I have 65 pieces. I need nine sheets to get it CNC, and I'm good to go. So these were just the size pattern experimenting. Nothing much. This is nothing great as such. Again, these are just very quick understanding of patterns. But this is how the sheet was. Now, the beauty was the design itself had these cutouts or these designs, which was used for binding it together. So what, if you see closely enough, if I show it to you again, right. So if you see closely, what is happening is you see these hooks. These are these MS hooks, which are used for pipes that you put it on the pipe and hold it on the wall pipes. We use those, we spray painted it in gold, in bronze, and used it to hold it together. The easiest part was, like, once we got this thing, we arranged it on the ground and rolled it. It literally became like a carpet. So it became easier for us to actually install and hook it up. So sometimes these are, so it looks quite complicated that one figures out, once one really wonders how one can do something like this. And coding would be a crazy aspect of it. Yes, it was, because later on I did want to code it. And the closest, the problem was you have a two-way curvature, and hexagons or any other material, any other shape, they in Grasshopper, you won't get a planar surface. And calculating a planar surface through kangaroo physics is quite complicated, and also computer hangs if you don't have a very powerful computer. Another thing is that if you don't want to do something like that, pardon me. So there's this wonderful series on about Somaya Museum of Mexico, and there they're actually using Arup used Python to actually, they used Kangaroo, and after that they had a Python script where they could actually make all these hexagons much more planar for their project. And that's a very massive script. If you get a chance to see that script, you should. But I couldn't afford those things because I didn't have the time, because my client did not give that time. So though she was sold with the idea, and the idea was that, okay, different patterns like a fabric, how do you change that? So that was what we sold, and this is what we could deliver, fortunately. I think I've covered most of the things which I did want to cover and share my knowledge with you guys. And I really hope that you guys could get some information about it. What I would like you to do is, for tomorrow, is take up a project that you have and just make something. So the first half, what we can do is we can have a question answer session where I can solve some of your problems, even if you have 2 or 3 options. So we can talk about it before we get into more detail into robotics then. I hope I wasn't too much And if you have any questions, we still have 5 minutes, 5 to 10 minutes we can talk about. All right. Does anybody have any questions or doubts or something that you wanted me to also talk about? Okay, all clear. Thanks, Yago.
So I'm just sharing the schedule for tomorrow of sorts. This is a rough along with the plugins required for robotics. So I think we'll start with Shashank's Q&A and the project discussion. Then go to the other components of it. All right. I'm just going to, 1 second, just while installing some of these plugins, make sure you'll check with the components. Shashank, I'm just going to take the screen a little bit. Give me a second. Yeah, okay. So in robot components, the plugin is readily available. The latest plugin you can opt for. Whereas in this robots, you can check this file out here. It will create an option. From here, you will get the main installation file also. If you have your own robot, setting that up will be it comes with a set of preset libraries. If you want to set your own robot, that will be slightly tricky. But if you have a model or something like that, we can go do a brief run through to set your own robot into this thing, because this has a slight tweak in the setup process. Apart from that, this is one plugin that you can check it, but do check out the GitHub link over the Grasshopper link. I think the GitHub link is more updated in this plugin in Machina. This plugin is option, Bengish. If we get time, we'll have a look at it and to see how we can develop some workflow with it. Apart from that, I'll be showing some components, some part of that in Robot Studio. If you don't have to download it. It's not a free software, but you do get a trial version for 30 days. But or else we'll be using some portions of the free part as a free part. We won't be getting into too much details of it. We will be yeah, trying. Sorry, Diego, will be the exercise about robotica. Yes, we will be covering a couple of exercises tomorrow, particularly to do with milling. One exercise in milling, one exercise in probably printing, and maybe one in pick and place. So these three things, I think we will hope to cover basically. And then, yes. All right, this is just what I wanted to say clear. Shashank, back to you.
Can you guys hear me? Oh, now you can. Yes. Okay, now yes. Okay, I'm so sorry. I'll just repeat myself. So Loki had a question about like how was the curvature preserved while fixing the ceiling. On the computer, what we see, and on site when you go, there's a massive difference. And yes, we could preserve roughly around 60 to 65% of the shape that we wanted. But apart from that, we couldn't. The problem also was that when we realized that how the clips that we were using between the two pieces, the clips, they had their own tolerances, and they also did not allow us to bend quite a bit. It did allow us to bend almost 90%, like at least a turn around to 90% to whatever degree we wanted, but that 10% was still missing. And so these things we do not understand through computers. We do understand by making it. But yes, we were happy because we could achieve the almost 60% to 65% of the desired shape that we wanted, with a little bit of kinks here and there. So eventually it came out to be perfect. And the number of pieces that I had calculated was actually more than enough. We saved almost around 75 pieces. 75 pieces were extra. So it was a good understanding of like what happened, so that and it wasn't very like the client was like, it's actually not a waste because we could use that somewhere else, and we did use those 75 pieces somewhere else. So it wasn't really a waste. All right, Diego, is this useful for the plain CNC milling? Okay. I didn't understand what do you mean by plain CNC milling. Right. So Loke, I mean, just not only Robotom. Diego, I'm so sorry. I still did not understand your question. Can you rephrase your question? Till that time, I'll answer Loke. So the ceiling was quite simple. So you have ceiling anchors, which you get in the market very readily available. So at equal intervals, we added these ceiling anchors. And what we did was at the start of it. So let's assume that this is your wall. And this is where my entire roll is, which is on the ground. I have to lift it up, right? So I've rolled it up and taken the starting part of it, and two people at two ends, they just lift it up. So what happens is, I'll find a video so that I can share it to you tomorrow in the morning. What happens is that these 2 points, we anchor it first with string. So you already have an anchor, which is like a U anchor like this. What we do is we take a GI wire, throw it around because there's already perforations in the pieces. You take the GI wire and fix it. So it's as simple as a basic GI wire. It takes the load completely, and also because it's at equal interval that we had this anchor points. So at every anchor point, so we calculated that every 2 feet we have the anchor, 3 feet we have the anchor point. So at those points, we had this GI wire, which is taking up that load. And because it's GI wire, the beauty was we could, once, or this is the wall again, and this is the piece, and now the piece is going up slowly and steadily like this. Now it's sagged like that. So wherever we wanted to pinch it up like that, in between, we could easily pinch it up, and we could play around with it because it's all GI wire. We could easily play around with it, and we had given enough tolerance, like enough leeway for it to flow around here and there. So yes, that entire assembly, like going on top on the ceiling, or hooking with the GI wire, was quite simple. That did not take much time. What took time was getting that flow right. So we spent a lot of time just to take out, like loosen the GI wire here or there, and like getting that flow right. That was quite like looking through the eyes and like seeing like, yes, yeah, you were liking it or you're not liking it and things like that. So that was a very much a design aspect of it. Right. So I hope that I'll share a video. I did not get it, unfortunately. So I'll share a video in the first thing tomorrow. So at least you'll see how the entire process happened. Diego, do you want to speak up for your question? Okay. Approaches is okay for any kind of CNC. Yeah, like you're talking about, yeah, okay. So you're talking about like 5-axis or 6-axis, like robotic arm is 6-axis. You also get milling machine on 6-axis. See, for 2D cutting, a normal CNC, you need a 2D file, basically. You need a AutoCAD 2D file, as simple as that. Anything 3D, you can use for 3, 4, 5, 6 axis machines. So that ranges from CNC milling to robotic arm or 3D printer for that matter. So anything like a rabbit, let's assume it's a rabbit, right? You want to mill a rabbit. You can use a 5-axis machine. You can use a robotic arm. You can use a 3D printer. So yes, so any type of CNC machine, you need for a 3D file, you need an STL, and you can actually create it according to that. So that's for 3D. Anything that, so the ceiling that you saw, it looks 3D, but it's actually composed out of 2D parts of it. Wherever you can create anything in 2D aspect of it, then you just need a 2-axis, a single-axis, 2-axis machine, which is X and Y, which is laser cutting, or even CNC can be done in 2-axis. For that matter, you can use, it's not that you can't use, I'll tell you where you will use robotic arm in 2-axis. So let's assume that, okay, hold on, give me a second. Wow, okay. Right, so there's a laptop in here, right? So the CNC, basically what it does is, you know, the CNC can cut like this, right? Now, it can't go like that. So this chamfer in here, this particular chamfer, so if you see my hand, I'm actually turning it around. So for this particular one, this file needs to be a 3D file. And I can send this file to a 5-axis CNC machine or a robotic arm, where I can actually get this thing cut. Many a times, because it's so simple, because it's a basic laptop in here, it's really nothing to do. It's just a rectangle and just one chamfer edge. I can still send this file as a 2D file, and I can tell the machine that the edges needs to be chamfered in a particular manner. So this part can turn around. So yes, there are ways where you can actually send a 2D file and yet do 3D milling into it. Yes, there is a possibility, but it really depends on design versus design. So like in the laptop case right now, which I showed you, because it's just the edges which are chamfered, most of the time tools are available which are chamfered like this, like the tools are chamfered in this manner. So what happens is that, again, going back to the laptop one, my tool will remain straight. I don't have to turn around because my tool itself is like in a V manner, so it can cut it around. We get tools which are chamfered on top, chamfered below. So literally in this particular shape. So you get, so it's known as an edge tool. So it actually goes, it's literally like a C shape, and it can go through like that. And these kind of tools are also used in lathe machine. So the same tools can be actually also fixed on a CNC. So it's not always required that. So to be very, very simple, any design which can be converted into a 2D can be used for laser cutting, like 2-axis, which is laser cutting and this thing. So 2D is basic Illustrator, EPS, or DWG file. So where you can send these files. Wherever you have a 3D, like a mountain, or like a chamfer or something, like, not a chamfer, like a mountain, or like a bottle, that is where you'll need a 3D file or an STL file. So that STL file, the same file, you can send it for 3D printing or for CNC milling or for robotic arm milling. I hope I answered your question, Diego.
Just to add to that point, if there is something that can be done with a regular CNC, it's best and faster to do it using a regular CNC and avoid the robotic arm, because you're adding more complication by trying to program the toolpaths using the robotic arm. And unless it's a really complicated 3D, like a sculpture of sorts, where you need to reach behind the sides of the ears and the underside of the nose, where it's hard to reach for a 2D CNC or a 3-axis CNC, only then would you attempt a more complicated system. So I think 80 to 90% of all the jobs can be done on a regular CNC, and using various strategies of cutting and or slicing together and combining two. And only in the most complicated of cases would you want to use your robotic arm and mount a CNC on top of it. It also takes considerably longer for the robotic arm to mill, because you are slightly more cautious of the speeds at which you're going to rotate the tool. Whereas the 3-axis CNC is pretty sturdy, and you have a very good direction and a tool path generated for it. Yeah.
Completely. I hope that answers quite a bit. I'll upload all the files in a bit so that you guys can at least try playing around with it. And if you have any other questions regarding milling, so first half we'll do some question answers, and also I'll show you a small example about how milling usually works, which also will give you clarity towards the next topic, which Sujay will take over on robotics then. And hopefully we try to give you enough information about like which tools will be easier and better for you for projects. So as what exactly Sujay just said, like which tools is better, when to use when, how, costing, and all those aspects of it. We would love to share those details with you. So do have your questions ready so that we can answer all of them. Right. So I think we should end for today.
Yeah. Sounds good.
Right. Thank you so much for your time, everyone. Let's meet tomorrow and let's talk again. All right. Thank you so much.
All right. See you all tomorrow.
See you all tomorrow. Bye.